Hello, I'm Anna Mackay and this video is on the rates of change in the applied calculus topic. So we've been differentiating and we're used to this terminology dy by dx, and it gives the rate of change in y with respect to x. We're familiar with this known as the derivative of the function, and it's telling us the rate at which something is happening. As an example, if we had dv by dt, that might be the instantaneous rate of increase in volume of, say, water entering a tank, where the units might be litres per minute, or in this notation here. So let's do two examples. First of all, we have the temperature of an object originally at 80 degrees Celsius. It's placed in a fridge. The temperature begins to fall according to the formula T is equal to T naught e to the power of kt, where T naught is the original temperature, T naught or T0, O for original I mean, and T is the time in minutes after the object is placed in the fridge. We need to find an expression for the derivative in terms of T. So we're writing out our formula here that T is equal to T naught e to the power of kt. And we know from the question, just going to draw that T again, that the original temperature is 80. So where we see this T naught, we're going to put in 80. So let's do that. Now we want to differentiate our function. So we're going to have d of capital T by d of little t. So with an exponential, you copy and paste what you see there, and then you differentiate the power. Now, we're differentiating in terms of t. Don't be put off by this k here, the coefficient of t technically. If you had to differentiate 3t, the derivative of that would be 3. So k is just any number, so differentiating kt, we just get k. Now, we might rewrite that with k at the front, and you can also see that part of the derivative here has the original function in it, which was t up here. So we can just resubstitute that in. So we've actually got k times by t. And that's something to be on the lookout when you're often doing these types of questions, particularly exponentials. Moving on. As you can see over here, I've just written what we worked out on the previous slide, that the derivative is k times by t. And here's our original function. So now we want to know that if the temperature is falling at 3 degrees per minute at the instant when the temperature is 50 degrees, find the time it takes for the temperature to fall to 20 degrees. So if you get one of these questions and you're a bit stuck, try and use what you've got there, all the numbers, and see if it might lead you to the answer. 3 degrees per minute. When you see something like per minute, that's telling you about the rate, and the rate is to do with the derivative. So when the rate is 3 degrees per minute and falling, that means our derivative, dt by dt, is equal to -3. So falling, -3 degrees per minute when the temperature, so that's capital T, is 50. So remembering this formula over here, we can now substitute those numbers back in. When our derivative, perhaps I'll just write it out here, is kt, and when our derivative is -3, we have k times by 50. So solving for k there, we've got k is equal to -3 on 50, which is equal to -0.06. So let's substitute k into our formula now. So for our function, 80 e to the power of -0.06 t. And the second part of the question asks us to find the time it takes for the temperature to fall to 20. So this time we know capital T is 20, and we're going to solve for t, little t. So let's do that. So write out our equation. 0.6t is equal to that 20, and we're solving. So go ahead and give that a go if you like. I'll push on with the answer. Solving for exponential equations here, we've got 20 divided by 80 which is a quarter. And if you log both sides here, putting a natural log on both sides, that's the equivalent of this line here. And now solving for t. I'm also, just for good practice, going to write that as 4 to the power of -1, just so that you get comfortable with working with your log laws. So we've got t is equal to, we have to divide through by -0.06. So that's, we could also write it as this, and 4 to the power of -1. And I might just tidy that up by bringing that -1 down out the front, and our time is equal to 1 over 0.06 ln 4, which is 23.1 minutes. So that is what the time would be for the temperature to get to 20 degrees. One last part, evaluating the derivative when the temperature of the water reaches 10 degrees. So again, remembering that our derivative is a multiple of the function, kt there. We know what k is now, it's -0.06. And when the temperature reaches 10, so that's our capital T, and the answer is 0.6 degrees. And what units might that be? Well, because it's the rate, it's per minute. And that's the end of that question. One more. Very, very serious question here. The quantity of a chemical which is responsible for animation of zombie corpses is given apparently by this formula here, where T is the number of days since becoming a zombie. So what do I mean by animation of zombie corpses? In terms of how much it's moving around. And I can tell you now that this is a decreasing function. So as the number of days go on, if the animation of this zombie hits 0, it's going to stop being animated and moving around, and therefore it's just a corpse, it's just dead. So a saying that I have is, let's create a visual, a picture. So we're going to graph this on our graphics calculators and use that to help work out these parts here. So I'm just going across to my new graphics emulator, and here's the function here. Now let's think about our view window. T was the number of days, so since becoming a zombie. So we're not interested in anything before 0 on the x-axis. And sometimes the question can give you an idea of how far along on your x-axis and your y to go. So it's interested up to 100 days, so we'll make sure we go to at least 100 on our x. But before we do that, let's think about how high up on the y it might go. When t is 0, or x is 0, let's think about what happens here. We've got 10 times by the square root of 0. Well, that's just 0. So our y-intercept will be 100. So let's make sure we go to 100, a little bit beyond to start with, and see if that view window does us. So we said 0 to, let's go 110 on our x. I'll do a scale of 10. Same on our y. I'm just going to go down to 0, and I'll start at 110 with a scale of 10. Draw that, and here's our function. So we're going to be working out these 3 sections here, and using the shift trace function on a Casio. If you put in 0 for x and enter, it tells us that y is 100. When x or t is 25, just hit that again. Once you've already pushed the trace once, you can just keep doing this. 50, so we've got 50 of the chemical in the system of animation of a zombie corpse. And when x is 100, which is 100 days, there is none left. So let's go and write these answers back for the question that we're doing. So when t is equal to 0, our y is actually an a. So we had 100. After 25 days, it's at 50. And at 100 days, we have 0 of that chemical left in the system. Moving on to do a bit more with this question. So we're finding the instantaneous rate of change. Now, just on that, whenever you see those words, that's the derivative. So let's differentiate this function. So I've just rewritten it in this form so that we can apply derivative rules. So the derivative is dA by dt. So differentiating this, that 100 disappears, becomes 0, and we'll differentiate the second part. So we get negative 10 times by a half t to the power of negative a half. Let's tidy that up a little, and we'll have negative 5 on the square root of t. And what do we need to do with that? We need to find the rate, the instantaneous rate of change when t is 16 and 25. So we're going to substitute those numbers into the derivative in two separate occasions and work that out. So when t is 16, and I'll do it here, when t is 25, our derivative dA by dt is negative 5 on root 16. Use your calculator or practice without it. Negative 1.25, and subbing in the second one. Now all of these answers are going to be negative, and we're going to have a think about that as to why. Thinking about that graph before, we had it was all going downhill. So we're getting negative values for our slopes, and that's what we would expect. Now, just a little side working out here, the average rate of change. When you see those words, that's telling you to do rise over run. So you need to do y2 take y1 over x2 take x1. These are our x values, and what are their corresponding y values? Well, when x is equal to 16, that one, I'll just tell you, is 60, and when x is equal, or t is equal to 25, we did work that one out on the previous slide to get 50. And there are values that we're going to use for the average rate of change formula and working that out. So we have 50 take away 60, y2 take y1 over x2 take x1, and that's coming out to negative 10 on 9, which is negative 1.11 recurring. So that's the average slope between those 2 points, and they're the instantaneous slopes. Moving on, and this is our last part, show that the rate at which zombies lose the chemical responsible for animation of zombie corpses is decreasing for all values of t. So when you get asked a question like this, it's asking you about the rate. So rate is the derivative. So let's think about our derivative. Feel free to just write it down. It's not t though, sorry. It's dA by dt. That was equal to negative 5 on the square root of t. Now, how to write this out? As t is greater than 0, why is t greater than 0? Because we're dealing with time. Because t is time, and it's the number of days since being bitten, so we're not going back in time, we don't need negative numbers. Let's think about the derivative function here, negative 5 on the square root of t. So if these values for t are always greater than 0, you're going to be getting the square root of what type of numbers? Positive numbers, which will always give you a positive number for the denominator here. So your rate is negative 5 divided by a positive number. So a negative divided by a positive will always give you a negative number. So that means that whole expression will always be negative. So we can say is always negative, or if you like, mathematically is always less than 0. So therefore we've just explained that the derivative is always less than 0, which is decreasing for all t greater than 0. And that matched with the graph that we saw, that it looked like it's always going downhill. So if you like this video, give it a thumbs up and subscribe to the channel, and the next video in this series will be called Optimization. Thank you.